Today we're going to look at redox reactions, which is another class of reactions that can happen, among other places, in aqueous solution. These are probably the most complicated to deal with, but they're not too bad, and you've seen them before if you've had another chemistry class. And so we're going to start out with some quizkins, and then we'll get into redox reactions in a bit. So as usual with the quizkin, we're going to have a problem. You pause the video and try and solve it, and then I'll put the answer up on the screen, and we'll see how you do. There will be 6 of these in a row, and they're all about predicting equations. Remember to use the techniques in the last video of checking first for acid-base reaction, then look for a gas-forming reaction, and then finally look for precipitation. So the first one is write an equation for a reaction, if there is one, that's going to occur when a solution of silver nitrate is added to a solution of sodium chloride. Pause the video, give it a shot, and I'll give you the answer in a minute. Okay, silver nitrate is AgNO3, and it says that this is a solution, so that's aqueous. Silver nitrate would be soluble because nitrates are all soluble. And it's reacting with sodium chloride, NaCl. It's a group 1 salt, so that's also soluble. It's aqueous. Well, acids and bases are not present here. Neither AgNO3 or NaCl are an acid or a base. And so either there's a precipitation or nothing's happening. If I look at the outside 2 species, the silver and the chloride, I have my precipitate. Chlorides, like all lower halides, are usually soluble, but with silver, lead 2, and mercury 1, they aren't. So AgCl is a solid here. That's my precipitate. The other species that's present is sodium nitrate, NaNO3, but that's a group 1 salt, and it's also a nitrate salt, so that will be aqueous. Try this one. It's ammonium nitrate added to a solution of sodium hydroxide. Ammonium nitrate, NH4NO3. That's a solid. You might not know that. It's added to a solution of sodium hydroxide, so NaOH, aqueous. What would happen? Well, NaOH is a base, but NH4NO3 is not an acid. So this isn't an acid-base neutralization. If I have a base, then I also look for ammonium, and I've got it. NH4, the ammonium ion, is the cation in this salt. When that happens with a base, you're going to get ammonia, gas, or you could write aqueous, and water, and a salt. And this salt is going to be the sodium from the base together with the nitrate from the ammonium salt, and that's aqueous. Try this one. What's going to happen, if anything, when potassium carbonate is added to sodium nitrate? Well, potassium carbonate solution is K2CO3, aqueous, and that's added to a solution of sodium nitrate, which is NaNO3, aqueous. Neither of these are acids or bases, so we're on to finding if there's a precipitation. If I put potassium together with nitrate, or with anything, it's going to be soluble because potassium is a group 1 salt. If I put sodium together with carbonate, or again with anything, it will be soluble. So I'm not going to get a precipitate, so what's happening is nothing. This is a no reaction. Try this one. Calcium carbonate added to a hydrochloric acid solution. Calcium carbonate is insoluble, so when I write CaCO3 here, I put a solid after it. And this is added to a hydrochloric acid solution. Hydrochloric acid is HCl, and AQ indicates that it's in solution. All right, what are my products? HCl is an acid. Calcium carbonate is not a base, so this is not an acid-base reaction, but it is a carbonate salt. And when carbonates react with acids, they give you CO2 gas and water and a salt. And the salt's going to be the cation from the carbonate, which is calcium 2+, and the anion from the acid, which is Cl1-, so CaCl2. Lower halides, like chloride, are almost always soluble, with a few exceptions, and so that's AQ. Barium carbonate solid is added to a hydrofluoric acid solution. So barium carbonate is BaCO3, and hydrofluoric acid is HF, aqueous. Well, HF is an acid, obviously. It's part of its name. But barium carbonate is not a base. So this is not an acid-base reaction. The next thing we check for is it a gas former? And it is. This is carbonate again, just like in the last example, and it's reacting with an acid. So that's going to produce for us carbon dioxide gas and water and a salt. And it's barium, which is 2 plus, with fluoride, which is 1 minus, to give BaF2. Is it soluble? I don't really know the rule for fluorides, so I'm just going to leave that phase symbol off. Try this one. Solid rubidium bisulfite, which also goes by hydrogen sulfite, is added to a hydriodic acid solution. Here's your answer. Rubidium bisulfite is Rb, and then bisulfite is HSO3. That's added to a hydriodic acid solution, which is HI, aqueous. All right, HI is an acid, but this is not a base. Rubidium bisulfite is a bisulfite, though. And bisulfites, when they react with acids, give us SO2, gas, and water, and a salt. And this salt is going to be rubidium as the cation and iodide as the anion. That's aqueous. Well, now it's time to start looking at redox reactions. Long ago, it was thought that there was a kind of reaction called an oxidation reaction, and an oxidation reaction was a combination of anything with oxygen. And then there were other reactions called reductions, and that's where oxygen was taken away. But we now know that oxidation is really defined more broadly than that, and where actually oxygen is involved is only a special case of what we call reduction-oxidation reactions. Here's how we define it now. Oxidation is defined as the loss of electrons by a chemical species. And reduction is the gain of electrons by a chemical species. These more broad definitions give us a lot more things that we can call oxidation and reductions that really are following the same pattern chemically. These can only happen simultaneously. You can't have oxidation without a reduction because the electrons can't be destroyed. They have to go someplace. And by the same token, you can't gain electrons unless they came from someplace. So these come in pairs or couples. And it's called a reduction-oxidation pair or a reduction-oxidation reaction. And we call that redox for short. By being oxidized, the species is giving up electrons. It's donating electrons to some other species. And that allows that thing to become reduced. So just like an insurance agent allows you to have insurance, or a real estate agent allows you to buy a house, a reducing agent allows you to get reduced. So species that are oxidized are reducing agents. Conversely, by being reduced, the species is gaining electrons, accepting them from somewhere else, which allows another species to get rid of its electrons and become oxidized. So we call things that are being reduced oxidizing agents. For example, let's take a look at this redox reaction. Here's the oxidation in this case. My 2 sodium atoms are becoming 2 sodium ions that are part of the NaCl. In order for that to happen, they had to give up 2 electrons. Here's the reduction. My chlorine molecule, Cl2, is gaining a couple of electrons so that each of the atoms can become a Cl- ion. Now, the Na plus and the Cl minus are what makes the NaCl. But the important thing to note here is that the sodium gave up the electrons that the chlorine needed. So it was a reducing agent for chlorine. The reducing agent in this reaction is the sodium. The chlorine accepted those 2 electrons, which allowed sodium to get rid of them. So chlorine is an oxidizing agent here. Now, in an ionic reaction that's very simple like this one, it's easy to see where the electrons are going, what lost electrons and what gained electrons. When we start working with molecules and polyatomic ions, it's a little harder to keep track of exactly what's being oxidized and reduced. So we have a trick for it. It's called oxidation numbers. If the oxidation number of an atom goes up during a reaction, then that was an oxidation. That species got oxidized. But on the other hand, if the oxidation number went down, then that's a reduction. So in order to be able to spot if oxidation or reduction are happening, we need to know what the oxidation numbers are. So I'm going to give you a set of rules for assigning what the oxidation numbers are in the reagents of a chemical reaction. First rule is the oxidation number of any uncombined element is 0. So if I have Fe in my equation or C, those would be zeros. But also something like H2 or N2 would be a 0. All these are 0 oxidation numbers because they're uncombined elements. Second rule, the oxidation number of any monatomic ion is equal to its charge. Mono means 1, so these are single-atomed ions. Like, for example, sodium plus. It's a 1 plus charge. Its oxidation number is also 1 plus. To avoid confusion, it's a good idea to write the oxidation number directly on top of the chemical symbol and put a circle around it so you don't get confused with the charge, because often both of them are going to be in the same general vicinity. Another example would be chloride ion, which is Cl1 minus, so its oxidation number is -1, just like its charge. Another rule, the sum of all the oxidation numbers of a polyatomic species, so that means a molecule or a polyatomic ion, has to be equal to whatever its charge is. So for example, let's say I had carbon dioxide. This is a neutral molecule, its charge is 0. So when I add up the oxidation numbers of the carbon and the 2 oxygens, they have to add up to 0. By the same token, if I had carbonate ion, CO3 2 minus, the sum of the oxidation numbers of the carbon and all 3 oxygen atoms would have to add up to -2. Another rule, this is a hard and fast rule, never fails. When fluorine is in a compound, its oxidation number is -1. Here's another rule, it's not quite as reliable, and that is that hydrogen usually has an oxidation number of +1. The only time it doesn't is when it's the 1 minus ion, H1 minus. And this shows up in something called metal hydrides. Like, for example, if I had calcium reacting ionically with hydrogen, I'd have CaH2 for my formula. But those are rare. You might not ever see those in this class. And so we can pretty reliably say that hydrogen is almost always +1. Another pretty reliable rule is oxygen most of the time has an oxidation number of -2 when it's in a compound. There are some exceptions. One of them is peroxide. Peroxide is actually on your polyatomic ion list, and it's O2 2 minus. In order for the rule about oxidation numbers adding up to charge to hold, the oxidation state has to be -1 here because there's 2 of them. And another one is superoxide, which is O2 1 minus. For 2 things to add up to -1, each one of them must be -1/2. So that's the actual oxidation number in superoxide. However, peroxide and superoxide are both relatively rare, and so most of the time, almost all the time, you're going to see it. Oxygen has a -2 oxidation state. Let's practice. Let's find the oxidation numbers of all the atoms that are in MoS2. Well, this is an ionic compound because MO is a metal and sulfur is a nonmetal. So the best thing to do when you have a case like this is split it up into its ions. So I have a molybdenum ion and I have the sulfide ion. Sulfide is group 6, so that means it's a 2 minus. If there are 2 2 minuses here, then the charge on my molybdenum must be 4 plus. Once I know what the charges are, it's easy to assign oxidation numbers because they're both monatomic ions. So sulfur is a -2 oxidation number, and molybdenum is a +4 oxidation number. Here's a polyatomic ion, the chloride ion, ClO2, 1 minus charge. Well, oxygen is almost always -2, so I'm going to assign that right here. -2 2 times give me a total of -4 oxidation numbers so far. All the oxidation numbers in all these species has to add up to -1 because that's the charge on the ion. So what do I add to -4 to get -1? +3. So that means chlorine has a +3 oxidation number in this species. One more. Vanadium 3 acetate. This is an ionic compound. I'll split it up into its 2 ions. Vanadium here must be a 3 plus because acetate is a 1 minus and it takes 3 of them to neutralize. The other ion is C2 H3O2 with a 1 minus charge. Well, vanadium's easy because it's a monatomic ion, so 3 plus is the oxidation state. Oxygen is usually -2, so I'll assign that. Hydrogen is usually +1, so I'll assign that. Now what do I have so far? -2 twice is -4. +1 3 times is +3. -4 plus 3 is -1. Well, the charge on the ion is also -1, and all of the oxidation numbers have to add up to that. So that means carbon here has an oxidation number of 0. Well, one of the most useful things about oxidation numbers is they allow us to find out where a reduction and oxidation is taking place. Once we've found that, we will often want to balance the redox reaction. Balancing redox reactions is not usually as simple as balancing the kinds of equations that we work with in metathesis and other kinds of reactions, double replacement reactions. And quite often, if you're starting out with a net ionic reaction, you don't even have all the species that you're going to need to ultimately balance the thing. So it's a good idea, it's almost an essential idea, to follow a set of rules, a technique for balancing these equations. One technique works in acid, and then we have to modify it slightly to make it work in a basic environment. So I'm going to teach you the steps of balancing redox reactions in an acidic environment. The first thing you want to do is assign oxidation numbers to everything, every atom in this equation, and divide the equation into two half reactions, one for oxidation and one for reduction. Let's take a look at an example. Here I have copper, which is an uncombined element. Its oxidation number would be 0. Next I have nitrate. Oxygen in there would be -2. -2 3 times would give me a -6. So that means my nitrogen must be +5 oxidation number because the whole thing has to add up to -1. Copper 2 is a monatomic ion, so its oxidation number is the same as its charge, which is 2+. NO, oxygen is -2, has to be add up to 0, so nitrogen must be +2 here. Now looking at the oxidation numbers, we can tell what's reduction and what's oxidation. Copper goes from 0 up to 2+, so that's an ox. The nitrogen in nitrate goes from +5 to +2 in NO, so that's a reduction. So I'm going to split this into my two half reactions. The first half reaction is Cu becomes Cu2+, and the second half reaction is NO3- becomes NO. This is the ox half. This is the red half. The next thing you do is, working with each half reaction individually, you want to balance all the atoms that are there other than H and O. So if I look at these two half reactions, that's already taken care of. There's one copper on each side in the first reaction. Second reaction, there's one nitrogen on each side. So that's irrelevant to this particular problem. Once that's done, you balance any excess oxygens by adding water to the appropriate side. So looking at my reaction here, the top half reaction doesn't have any O in it at all, so this is not a step that would be useful there. But the bottom half reaction has 3 oxygens on the left, but only 1 on the right. That means I need 2 more oxygens on the right. I can provide them by adding 2 water molecules. Now that screws up my hydrogen balance, but we're going to deal with that in our next step. The next step is balance excess hydrogen by adding H+ to the appropriate side. So looking at where we're at now, on the second half reaction we now have 4 extra H's on the right hand side. So on the left hand side I'll take care of that by adding 4 H+. Once that's taken care of, your next move is balance the net charge by adding electrons on the appropriate side. You will always be adding electrons in these reactions, on one side or the other. And really, they need to be on opposite sides, because this is a redox. It's not a red-red or an ox-ox. Looking at what we have right now, in the top half reaction, the left-hand side is neutral, the right-hand side is 2+. So if I add 2 electrons, which are negative, I'll make the right-hand side neutral as well. Second half reaction, the right-hand side is neutral. The left-hand side is 4 pluses and 1 minus, so that'd be 3 plus altogether. So to make it neutral like the right-hand side, I'll add 3 electrons to the left-hand side. Now my two half reactions are balanced, and the next thing I need to do is add them back together to make an overall balanced equation. Now I can't really do that right now because I am showing in my oxidation the loss of 2 electrons. But in my reduction I'm showing the gain of 3 electrons. That can't really be. I can't create that additional electron that the reduction needs. So what that tells me is this really isn't how this is happening in nature. The electrons lost and gained have to be the same. So we'll fix that. So our next step is multiply whatever you have to by coefficients to make the electrons balance, to make the number of electrons lost and gained be the same. Like in the reaction that we're at so far, I'm losing 2 and I'm gaining 3. Well, 2 and 3 have a least common multiple of 6. And so I'm going to multiply the top reaction by 3, and that will have me losing 6 electrons. I'm going to multiply the bottom half reaction by 2, and that will have me gaining 6 electrons. Once you've got that fixed, the last step is to sum the half reactions up, and then, if necessary, cancel anything that shows up on both sides of the arrow. So with the reaction I'm working with right now, I'm going to add these together and see what my overall reaction is. From the top, on the left-hand side, I have 3 coppers. From the bottom on the left-hand side, I have 6 electrons, but I know the electrons are going to cancel out, so I'm not going to write them down. 2 times 4 is 8, so 8 H pluses. 2 times 1 is 2, so 2 nitrates. On the right-hand side of the arrow, from the top half reaction, I have 3 Cu2 pluses. And from the bottom half reaction, I have 2 times 1, which is 2 NOs, and 2 times 2, which is 4 H2O. There's my balanced chemical equation.
When you balance redox reactions in a basic environment, you have to think about things differently than if you're balancing it in an acid environment. The same solution that worked for an acid environment won't work in a basic environment. Let's go back and take a look at our last example, and I'll show you why. Here's why right here. This H+, that can't exist in a basic solution, because if there's a base present, that's immediately going to react with those H+ and pull them out of solution. So this really can't be what's happening there. We'll have to take a different approach that accounts for the fact that we're in a basic environment if we're going to balance redox reactions in the presence of a base. So here's what we do. First of all, we begin by ignoring the fact that it's in a basic solution. Do all the steps for balancing the reaction in an acidic solution. So the first step, of course, is assigning oxidation numbers and then splitting up into half reactions. Well, for oxygen in the permanganate ion here, it's -2. 4 times that would give you -8. So if we're going to sum up to -1, the manganese must be +7. Moving on to oxalate, it's -2 for the oxygen. 4 times would be -8. So the carbons must be +6 to add up to -2 for an ion charge. So that means each one of the 2 carbons must be +3. On the product side, MnO2 will be -2 for oxygen. Twice would be -4. And since this is a molecule, the sum has to be 0. So +4 is the manganese oxidation state. And then carbonate. It's -2 for oxygen, as typical. 3 times would give me -6. So the carbon here must be +4 if the oxidation numbers are going to add up to -2. So we can identify the half reactions here. Manganese is going from +7 in permanganate to +4 in MnO2. So that is a reduction. And carbon is going from +3 to +4 when it becomes carbonate from oxalate. So that's the oxidation half reaction. So let's set up our half reactions and continue to balance. So one half reaction is MnO4- becoming MnO2. That was my reduction half reaction. And the other one was oxalate, C2O4 2- becoming carbonate, CO3 2-. Okay, looking at the top half reaction, the manganese is already balanced, so we can move on to oxygen. I balance oxygen with water, so I need 2 more waters on the right, so I'll put 2H2O. That gives me 2 oxygens to help bring oxygen into balance. That gives me 4 hydrogens on the right that aren't on the left, and so I'll add 4H+ to balance that on the left. and then I have to balance charge. The right side is neutral. The left side is 4 pluses and a minus. That's 3 pluses. So 3 electrons would make the left side neutral and match the right side. Moving to the second half reaction, the oxidation, I have 2 carbons on the left but only 1 on the right. So I'll balance carbon by putting a 2 in front of carbonate. That gives me 6 O's on the right. On the left I have only 4 O's. So that means I'm going to need additional oxygens on the left. 2 more, in fact, so I'll add 2 waters because that's how I balance oxygen. That gives me 4 H's on the left. On the right there is no hydrogen, and so I'll put 4 H plus to balance that. And then I have to balance charge. On the right hand side I have 4 minus and 4 plus, so that's neutral. On the left hand side I have 2 minus, so that means to make this balance I have to add 2 electrons to the right hand side. Now I'm losing 2 electrons in this oxidation, but I've gained 3 in the reduction on the top half reaction. So in order for these to sum together, the electrons lost and gained have to be the same, so I'm going to multiply the top reaction by 2 to get 6 electrons, and the bottom by 3 to get 6 electrons. Now I can sum these up because the electrons are going to cancel out. So 2 times 4 is 8, so I have 8H plus on the left, plus 2 permanganate, plus 6 water, because 3 times 2 is 6, plus 3 oxalate, C2O4 2-. On the product side, 2 MnO2s, and 2 times 2 is 4 waters, and 6 carbonate, and 3 times 4 is 12 H pluses. Now I can clean this up a bit because I have 8 H pluses on the left and I have 12 on the right. So I can just get rid of the 8 on both sides and change the 12 to a 4 H pluses. And the same thing is true for water. I have 4 waters on the right and 6 waters on the left. So I'll just subtract 4 waters from both sides, and that leaves me with 2 waters. So I'll rewrite this to clarify. 2 MnO4 minus plus 2 water plus 3 C2O4 2- gives 2 MnO2 plus 6 carbonate plus 4 H plus. Now we've got that problem again. We have H plus in our balanced equation and we know that it can't exist. So the next thing we do is we add to both sides of the equation the same number of hydroxide ions as there are H pluses. And we can do that because that's basically what the acid-base reaction that will ensue is going to do. So looking at our balanced chemical equation here, we have 4 H pluses on the right. So we're going to add 4 OH minuses to the right. But it's not an equation anymore unless we do the same thing to the left. So we have to add 4 OH minuses on the left as well. The next thing we do is we combine the H plus and OH minus, just like nature would actually do this in a chemical beaker, to form water. So summing these up, we know that the H plus and the OH minus is going to make water now. So I'm going to write 4H2O, 4HOH. On the left-hand side, I now have 4OH minus plus what I had before, 2 MnO4 1-, 2 water, 3 oxalate, 2 MnO2, and 6 carbonates. Then the next thing I want to do is cancel away anything that appears on both sides, and this will often happen when you do this last step. Water is commonly on both sides. So I have 4 H2O on the right, I have 2 H2O on the left, and I can clean this up by just subtracting 2 waters from both sides. So my overall balanced chemical equation is now 4OH minus, and it's okay to have OH minus because that's what would be present in a basic solution, plus 2 permanganate plus 3 oxalate produces 2 MnO2s, 6 carbonate, and 2 waters. Okay, I'm going to give you a couple of opportunities to practice. Try doing this one. This is permanganate reacting with iron 2 to produce manganese 2 ions and iron 3 in an acidic environment. Stop the video and give this an honest try. Follow the steps and see if you can come up with a balanced chemical equation. I'll flash the balanced chemical equation up on the screen here, and if you got it right, move on to the next one. Otherwise, watch my solution. Okay, here's my net ionic equation. This is my starting point. My first step is I want to assign oxidation numbers to everything. Well, for oxygen in permanganate, that's going to be -2. -2 4 times is -8, so the manganese must be +7 if the whole ion has a -1 charge. Everything else is easy to do because they're all monatomic ions. So iron 2 is 2+, manganese 2+ is oxidation number 2+, and iron 3 has an oxidation number of 3+. Well, you can easily see what's happening here. Permanganate is reducing, and the iron 2 is oxidizing to iron 3. So I'm going to split this into half reactions at this point. So the reduction half reaction, MnO4 1- becomes Mn2+, and the oxidation half reaction, Fe2+ becomes Fe3+. Working on the top half reaction, Mn is balanced, but oxygen isn't. I have 4 extra O's on the left, and so I'll add 4 waters on the right. That gives me 8 H's on the right with nothing on the left, and so that means I need 8 H pluses to balance that on the left-hand side. Now, balancing charge. The right-hand side is 2+ total. The left-hand side is 8 pluses and a minus, so that's 7+. To get 7+ reduced down to 2+, I need to add 5 electrons, so that's what I put on the left-hand side. Second half reaction. Iron's the only thing you have to balance, and it's already balanced. Now I have to balance charge. It's 2+ on the left, 3+ on the right. 1 electron on the right will bring that into balance. The electrons gained and lost are different. 5 gained in the top reduction half, and the bottom oxidation half loses only 1, and so that's not how it really works. I'm going to have to use coefficients to change this. So I'll multiply the bottom half reaction by 5, and then 5 electrons are going to be lost, and 5 will be gained, and the electrons will cancel out. Now I sum the reactions together. Electrons are gone. It's 8H+ on the top, plus permanganate, plus, from the bottom half reaction, 5 Fe2+. On the right-hand side, from the top, it's Mn2+ and 4 waters. And then from the bottom, 5 Fe3+. Well, this is an opportunity for you to do one in a basic environment. I've got CrO2 1- and the hypochlorite ion reacting to form chromate, CrO4 2- and chloride ion, and this is happening in a basic environment. Stop the video, try your best to get yourself a balanced chemical reaction in a basic environment, and I'll put the answer up on the screen if you need to look at the solution. Well, my first step is assigning oxidation numbers. For oxygen, that's going to be -2 in the CrO2 1-. 2 of those would be -4, so that means the chromium must be +5 in this species. Moving on to hypochlorite. Oxygen's -2 as always. To get back up to -1, well, the chlorine must be +1 here. Dichromate. -2 for oxygen. -2 4 times is -8. So the chromium must be +6. So the oxidation numbers can all add up to -2. And then chloride is a monatomic ion, so it's just -1. Well, here's our oxidation. CrO2 1- goes to CrO4 2-, and the chromium oxidation state goes from 5 up to 6, so that's an oxidation. So the reduction is the chlorine species, and chlorine's going from +1 to -1, so that's definitely a reduction. So I'll write down my half reactions. CrO2- goes to CrO4 2-, and then the other half reaction is ClO 1- becomes Cl 1-. On the top half reaction, the oxidation, chromium's already balanced. I have 4 O's on the right, but only 2 O's on the left, so I'll add 2 waters to make that oxygen balanced. That gives me 4 H's, so So I'll balance that by putting 4H plus on the right-hand side. The left-hand side has a 1 minus charge. The right-hand side has 4 pluses and 2 minuses, so that's 2 plus. So that means I need 3 electrons to balance charge. Moving to the second half reaction, chlorine's already balanced. I have 1 O on the left, none on the right, so I'll add water to balance that. And that gives me 2 H's that I don't have on the left, so I'll add 2H plus on the left. The right-hand side is 1 minus. The left-hand side is 2 pluses and a minus, so that's 1 plus. To get from 1 plus down to 2 minus, I would need to add 2 electrons on the left. Well, I have 3 electrons lost in the oxidation and only 2 electrons gained in the reduction, so I have to modify this by putting a 2 in front of the top half reaction and a 3 in front of the bottom half reaction. Now when I sum, the electrons will be 6 and they'll cancel from both sides. What's left? Well, 4H2O is one thing, 2 CrO2 1 minus, 6 H plus, 3 ClO minus, 2 CrO4 2 minus, 8 H plus, 3 Cl minus, and 3 H2O. I can clean this up a bit. I have 3 waters on the right and 4 on the left, so I'll subtract 3 from both sides, leaving me with just 1 water on the left. I can do the same thing with hydrogen. I've got 6 H's on the left and 8 on the right, so I'll take 6 from both sides, leaving me with only 2 H pluses on the right. Now this happened in a basic environment, so the next thing I have to do is identify that I have 2 H pluses present on the right and add to that side 2 OH minuses. But I can't do that only on one side or it isn't an equation anymore, so I'll add 2 H minuses on the left as well. What does that leave me with when I sum it all up? Well, the left-hand side now has 2 OH minus and 1 water and 2 CrO2 1 minuses and 3 hypochlorites. On the right-hand side, it's 2 CrO4 2 minus. The 2 H pluses and the 2 OH minuses now make 2 H2Os, and I've got my 3 Cl minuses. I have a water on the left and 2 on the right, so I'll just get rid of that water and make 1 water on the right, and there's my balanced chemical equation. I'll rewrite it for simplicity. 2 OH minus plus 2 CrO2 1 minus plus 3 ClO 1 minus makes 2 CrO4 2 minus and a water and 3 chlorides. Well, hopefully now you have some skills that you didn't have before, or at least were rusty with, and now you can balance a lot of redox reactions, which are complicated. They're not as easy to do as balancing other kinds of equations, but you've got a pretty good skill set now. In our next video, we're going to take a look at how we can use numbers to quantify the strength of a solution, and then put that together with what we know about reactions in solution to develop a very powerful and common lab technique called titration.